This is a video for AQA Further Pure Mathematics. This is Vectors section 2.1. We're looking at the vector equation of a line in 2 dimensions. The general form of a vector equation is r is equal to a plus lambda d. So r is a point on the line, and we're trying to find an equation for its position vector. The components of the right hand side of that are such that the A is a position vector of a point on the line. So that if we were to draw a vector from O to the line, where this is the point A, then there's the position vector of that point. So if we've got a known point A, then that makes up the first part of the general equation. The next part is that we have a scalar multiple, so lambda, of a direction vector. So if I mark a direction vector on here, let's say that there is d, then for different values of lambda we would have different points on the line. So for example, that one there would be lambda equal to 1, and the one along would be lambda equal to 2, this one here lambda equal to 3, and so on. And coming backwards, of course, we'd have lambda equal to -1, etc. Where lambda can take any value. It doesn't have to be whole numbers, it can literally be any real number. And that then will give us a position vector of any point on that line. So we've got these two main parts. A is a known point on the line, and then D is the direction vector. So as an example of that, then let's find the vector equation of this line, which passes through the point -3, 2, so that's our known point, and in the direction 2i plus j, so we have 2 along and 1 up. So therefore our vector equation is r is equal to the known point, which is at -3, 2, and then lambda multiplied by our direction 2, 1. So for example, if we look at the point up here at the top there, we can see that that is going to be at lambda equal to 3. So when lambda equals 3, we have that r is equal to -3, 2 plus 3 times 2, 1, or in other words, plus 6, 3, and that is at 3, 5, which is that point that I've indicated at the top. So for any given value of lambda, we will have different points on that line. Well, sometimes we're not given a direction vector directly. In fact, a line can be defined by just 2 points. If you think about it, if we have 2 points that line a line, we've uniquely defined the line. So here's an example of that. We've got the line going through the points A and B, where we've got A is equal to 3, 2, and B is equal to 2, -1, the position vectors of A and B. We can choose either of A and B as our point on the line, and we can calculate the direction vector by taking the vector between the 2 points. So for example, we could use B as our known point and the vector from B to A as our direction. So if we wanted the vector BA, then remember that would be the position vector of A minus the position vector of B. So we would have the vector 3, 2 minus the vector 2, -1, and that gives us 1, 3. And clearly that's correct. You can see that on the diagram that the vector BA is indeed 1 and 3. So therefore our equation is equal to the position vector of one of the points, 2, -1, for example, plus lambda times the direction vector 1, 3. Now clearly there are many options for this. If we used a different starting point, we would have a different equation. If we used a different direction, a parallel direction, but maybe a multiple of the one we've used at the moment, that indeed would also give us the same equation. So the actual equation of a line is not unique. We can alter it around to have different starting points and different lengths for the direction vector. Well, in summary then, we have that the vector equation is of the form r equals a plus lambda d, and we've just said that this is not a unique thing where a and d can actually be different, but will define the same line. Two lines are going to be parallel if the direction vectors are the same, or if one is a multiple of the other. And two vector equations are going to represent the same line, what we say is collinear, if they are parallel and share a common point. And finally, if d is a vector d1, d2, then the gradient of that line is given by d2 over d1. This is the end of the video vector equations in 2 dimensions. In the next video we'll look at equations of a line in 3 dimensions.